All right, John, so we're going to continue on and we're going to move on to the next section of probability, which is the probability of exactly R successes in N trials. And these are the kind of questions that you're going to encounter the most on the test. These are the kind of questions that people more often kind of associate with probability questions, with the probability chapter. And a lot of times people look at it and be like, I have no idea how to do that. But all it is a pattern, and pretty much you're going to set up these questions exactly the same way every single time, and different questions just have different numbers, but you're doing the same thing every single time. So it's really not as difficult as people make it out to be. So what we're going to do is we're going to talk about a Bernoulli experiment. This stuff really isn't that important. It's just kind of technicalities, also known as a binomial experiment, blah, blah, blah. Must meet the following conditions. There are exactly two outcomes. So like we're talking about the probability of a team winning a certain number of games. So there's two outcomes. Either they could win or they could lose. It might be flipping a coin. Either it's a head or it's tails. It might be rolling a dice. You either get a number 2 or you do not get a number 2. There's always only two outcomes. There is a fixed number of trials, that is N. That is, like always, what we've been talking about with NCR, with NPR. That N, oh, that's supposed to be a P. That N represents the total number, and it still represents the total number. Nothing has changed. This time it's just the total number of trials that we're completing. So I'm flipping a coin a total of 6 times. Or I'm rolling a dice a total of 10 times. The trials are independent, meaning that I roll a dice one time and I get a 6. And now that 6 does not affect the next time that I roll the dice. You know, my probability of getting a 6 is not going to change because I got a 6 the first time. And the probability of each outcome is the same for each trial. And I know that, yet again, it sounds really weird to hear all this stuff from the beginning, but I'm going to explain what I mean as we go along. Those are more kind of like just the technical definitions of what we're doing. We have a formula for this, and I'm going to explain this formula in a second. NCR, and then in parentheses you're going to put the probability of success raised to the R power, and then in another set of parentheses we're going to put the probability of failure raised to the N minus R power. You may write this down right now if you want to. I'm going to kind of go through and explain it just a little bit differently or better than this formula does, but you are more than welcome to write it down. This is what we're talking about. These are the kind of questions that we're talking about when we're dealing with probability. A fair coin is tossed 3 times. Find the probability of getting exactly 2 heads. Okay, well, this is how I like to set it up from the beginning, and then we're going to kind of manipulate or change our process to kind of fit more so the formula than just this. So we tossed it for a coin 3 times. So 1, 2, 3. Find the probability of getting exactly 2 heads. So I want heads, heads, and I want tails. Now what's the probability that I get a heads when I flip a coin? Well, a coin only has a heads and a tail. So the probability of getting heads is 1/2. And the probability of getting heads over here is still 1/2 because those trials are independent of each other. Nothing changed. And the probability of getting a tail is actually 1/2 too. Okay, so what I would normally say is, alright, we can just multiply 1/2 times 1/2 times 1/2, and there you go, done. Except for, here's the problem that we have. What we just found is the probability that we get a head, and then a head, and then a tail. We didn't take into consideration the fact that we could get head, tail, head, or tail, head, head. So there's a bunch of different combinations of ways that we could get 2 heads when we toss a coin 3 times. So in order to account for that, we did a total of 3 trials, and we're trying to figure out the different ways that we could make a combination of 2 heads. Okay, so we're still multiplying all these things together. It's just that we're going to multiply 3, choose 2 out front. That way it'll take into consideration all the different ways that this could happen. Okay, so let's come over here. 3, choose 2. That gave us a 3. So 3 over 1 times, and then I can multiply across the numerators, that's still a 1, and then across the denominator, 2 times 2 is 4, times another 2 is 8. So the probability, if I tossed a coin 3 times, the probability that I get exactly 2 heads is 3 out of 8, 3/8. And typically what we're going to do is leave it as a fraction unless they ask otherwise, okay? Now we're going to figure out the probability of getting exactly 3 heads. So I'm going to toss a coin 3 times again. This time I want to get 3 heads. Now what's the probability of me getting a head? It's a 1/2. What's the probability of it here? That's 1/2. And that's 1/2. And this time I need the combination of all of these, which is actually really kind of silly this time because 3 choose 3 is actually just 1, so we're really just multiplying by 1. But I just want to have you put it in there to get used to doing this. So 3 choose 3, you can check in your calculator if you want. That's going to give you a 1. 1 times 1 times 1 gives me another 1. 2 times 2 times 2 gives me 8. So exactly 3 heads, that's 1/8. I don't know why they asked exactly 1 tail because that's the same thing that we found up here. But what I do want to do right now, let's change this to 2 tails because we haven't found that yet. What I want to do is kind of take this process that we've been doing and I want to kind of manipulate it or morph it back into this version. And I'll show you what I mean. Now, we're going to find exactly 2 tails. So, 1, 2, 3. 2 tails. So I want tails, tails, heads. 1/2, 1/2, 1/2. And I'm going to do total of 3 tosses, but I want 2 of them to come out as tails. Now 3 choose 2, we already found out that's a 3. But what I want to do right now is I want to kind of change this into the process that you would use in class. Now the first part out front, NCR, that doesn't change at all because we've gotten used to doing that anyways right here. 3 choose 2. So this is how we're going to do it more often on a daily basis. 3 choose 2. Now what we're going to say is, what is the probability of success? Well, in this case, our success was getting a tails, right? So in this case, our probability of success is to get a tails. And the probability of failure is not getting a tail. Well, obviously, in this case, not a tail is just a head. But the probability of getting a tail, that is 1/2. And the probability of failure of not getting a tail, that's 1/2 as well. So we're going to put the probability of our success in parentheses and the probability of our failure in parentheses as well. Now what we're going to do is we're going to raise this. This is our success. What we're going to say is how many times do we want to be successful? We want exactly 2 tails. Therefore, we want to be successful 2 times. How many times are we going to be not successful, or how many times are we going to fail? We're going to get heads once. So you can see that the way that I just set it up is still exactly what we have up here. 1/2 times 1/2, the tails times a tail, that just kind of converged into one little thing of 1/2 raised to the second power. It's still the same thing, 1/2 times 1/2. And then the probability of failure, that was our head, that's just 1/2 to the first power. The reason why we do this is just because when you get to more complicated problems, it's going to be a lot easier. So we know that 3 choose 2 is a 3. So this is 3 over 1. And then what we do not want you to do is to put these numbers as fractions into your calculator. Let me say that again. Do not put these numbers as fractions into your calculator. You are going to do them out separately. Okay? Because when you put them in your calculator, the calculator simplifies the fraction, and that's not what we want, because the answers on your test and the answers on the Regents exam will not be simplified. So if you have a binomial squared. It's really 1 squared divided by 2 squared. 1 squared is just 1. 2 squared is 4. The same thing over here. 1/2 raised to the first power is just 1/2. And then you can go ahead and simplify it just like we did before. Multiply across the top, that's 3. And then across the bottom, that's 8. It looks more complicated just because we already knew what the answer was up here, but it's really not more complicated. I'm going to show you more problems like this. Alright, a die is rolled 4 times. What is the probability of getting exactly 2 6s? Now that I kind of broke that down for you and explained how to do this, I'm going to start by setting up a pattern. We're going to do the exact same thing every single time. What is our n in this case? What is the total number of trials that we have? In this case, our n, our total number of trials is 4 because we're rolling the dice 4 times. What is our r? Well, what is the probability of getting exactly 2 6s? So we're looking to get a 6, roll a 6, 2 times. So this is our r right here, 2. So we're rolling 4 times, but we want to get a 6 twice. Then I want the probability of success, which in this case, the probability of getting a 6, and the probability of failure, or not getting a 6. So if you have a die right here, what's the probability that you roll a 6? Well, a dice has 6 sides on it, so the probability that you roll a 6 is just 1 out of 6. Versus not getting a 6, meaning you could get a 1, 2, 3, 4, or 5. That's a 5 out of 6. Alright? You're going to use every single piece that you have over here to set up your equation. The first part of our equation was always the combination. I'm doing NCR. So 4 is our N, C 2. You don't even have to think about it once you set this up. 4, choose 2. Then in parentheses, my probability of success is 1/6. How many times do I want to get a 6? I want to get a 6 twice. Then my probability of failure. How many times am I going to fail? Well, if I have a total of 4 rolls that I'm doing, and I'm going to get a 6 twice, how many does that leave me left over to not get a 6? That leaves me 2 times left over and not get a 6. Now I set up my equation. Now I'm just going to go through and simplify everything. 4, choose 2 is 6, and I'm going to write it as 6 over 1 because these are all going to be fractions. 1/6 squared is the same thing as 1 squared divided by 6 squared. So 1 squared is 1, 6 squared is 36. Times 5 squared, which is 25, divided by 6 squared, which is 36. Now, I'm not putting these fractions into my calculator. I'm simply multiplying across. 6 times 1 times 25 gives me 150. Divided by 1 times 36 times 36 gives me 1,296. Now let me show you what I mean by not putting it in the calculator. 150 divided by 1,296 can be reduced as a fraction as 25 over 216. That will not be an answer on the test. This is what will be an answer on the test. So that's why I don't want you to simplify this. Okay? We're going to do more problems when I come back.